So now that we've defined work and the relationship between force, the angle it makes, and the distance it moves, delta x, let's look at something called the kinetic energy and work kinetic energy theorem. In this, we state that if the work done by the net force on the object can be calculated for a given displacement, the change in the object's speed is easy to evaluate. So this is why we're back to our motion equations. So if we go back to what we just defined, but this time we're going to call it the net work, okay? And we're going to say that it's equal to the force times the distance, okay? There's an understood cosine theta in here. Remember that we have force, which we defined early on as mass times acceleration. Now we have a relationship here that we can use to use some of these motion equations. So if we pick the correct motion equation, we might be able to do a substitution in here and come up with something to help us solve other types of problems with work and energy. So now we have mass times acceleration times the distance. So if we go back and choose one of our relationships that has something in it that looks like this mass times acceleration times the distance, you can see over here 2 times acceleration times the distance is exactly a term that we could use for a substitution. So the velocity final squared, remember there's an understood final there, velocity final squared is equal to the velocity initial squared. And remember, sometimes that velocity initial squared is 0. If you start at rest, that's 0. So all of that term would disappear anyhow. Times or plus 2 times the acceleration times the distance. So let's take this and move our terms around here so that we have the acceleration and the distance on one side of the equation and everything else on the other. So if we move the velocity squared to the other side, velocity initial squared to the other side, we subtract it, and then we divide both sides by 2. We end up with acceleration times distance is equal to velocity final squared minus velocity initial squared. Again, typically that term goes away and you're left with velocity final squared over 2. So now we can go back to our definition that we put forth on the top here. The net work is equal to, factor out the mass, we have acceleration times distance is equal to mass times velocity final squared minus velocity initial squared divided by 2. Now what I can do is I can factor out the 2, or the 1/2 in this case, from both of those terms so that I now have a definition that says the net work is equal to 1/2 mv squared, that's the final term, minus 1/2 mv initial squared. Okay? So what we end up with here then is a term, like I said, most of the time this term goes to 0, is now we can call this kinetic energy. So we have another term that we can use that we call kinetic energy is equal to 1/2 the mass times the velocity squared. So we can look at this then by breaking it apart and saying, well, then the first term would be kinetic energy final minus kinetic energy initial. And you'll get used to using these in your analysis and your work. So the net work done on an object by a net force acting on it is equal to the change in the kinetic energy of the object. Okay, so what we're doing is we're using these relationships that we've learned to try to build new tools to help us solve for certain types of problems. Okay, so let's look at a problem. Typical problem that would use this expression. We've got a 1,400 kilogram car that has a net forward force of 4,500 newtons applied to it. Okay, so the car's rolling at 4,500 newtons. Okay, the car starts from rest and travels down a horizontal highway. What are its kinetic energy and its speed after it's traveled 100 meters. Now we're going to make some assumptions here. We're going to ignore any losses in kinetic energy because of friction air resistance, because it would be too difficult to factor these in. So we're going to ignore friction. So if we look at the relationship here, we see that we set the mass equal to 1,400 kilograms. We set up our free body diagram here, as an example, normal force up, weight down, and we've got the force of the vehicle, 4,500 newtons applied to it. Okay, and it's moving in the direction delta x, which we're going to use 100 meters for that. So let's start with our defined net work. So the work net is equal to 1/2 mv squared minus 1/2 mv initial squared, and we are going to assume, since it said it started at rest, that v initial is in fact equal to 0. So all of that term, everything on that side goes to 0. So the net work then is equal to force times distance. So 4,500 newtons of force, distance 100 meters. We have a net work being done by the car of 4.5 times 10 to the 5th joules. Okay, it's good to get used to using our metrics here. So now we can go back to the other equation with the motion in it, and we can solve for the velocity, because they ask us what's the kinetic energy and they say speed, what is the velocity after it's traveled 100 meters. So now we can say that since in the initial part went to 0, all I'm left with is 1/2 mv final squared is equal to that 4.5 times 10 to the 5th joules. So if I move the 2 to the other side, okay, multiply both sides by 2, I get velocity squared final by itself. Now I have 2 times that value in the numerator, and I divide it by 1,400 kilograms because I'm going to move the mass into the denominator. Take the square root of both sides. I get the square root of 643 meters squared per second squared. And when I take the square root, I get 25.4 meters per second. So you can see how we're using all of these tools to help us solve for different types of problems. Again, make sure you're keeping track of this in your notebook so that you've got a quick place to get to these types of relationships and examples to rely on to help you understand how this all works. Okay, so we've looked at kinetic energy. When we come back, we're going to look at potential energy. Remember, that's the energy due to position in space.